next is an ecologist, because one of the things that we're thinking about from a biomimetic perspective is what is all of the data that goes into these models, and where does that come from, and what does it mean to gather that data, especially if we're drawing from other ecosystems, if we're drawing from ecological systems and saying, yes, this is the carbon that should be fixed, yes, this is the amount of water, and if we've got a reference ecosystem, what does it mean to have a reference ecosystem? And in North America, we have the advantage of these long-term ecological research sites. And Dan comes to us, who is a wetland ecologist in the desert, but was managing the LTER in the Everglades, and is now heavily involved in the LTER here in the Sonoran Desert. So I'm hoping Dan can give us some perspective on what does it mean to actually gather this data in the first place. Okay, thank you.
Right. That's me. Yeah, how it works. So, I really hate microphones, but I think I need to use it, right? So I'm just going to stand way back here. I want to talk about a concept very, very briefly, about a concept called urban ecological infrastructure in the context of the ecosystem services that it provides to urban ecosystems. And as Dana said, the overall picture that I'm going to present this from is from 20 years of NSF support for our Central Arizona Phoenix LTER program. And so the question that's guiding our research right now, which you see on the board here on the screen, I'm not going to read it to you, but it's a very cyclical question. As you read through it, you can see that it cycles between the human and the biophysical components of the system. It's very focused on urban ecological infrastructure, which I will define for you in just a moment, and the ecosystem services that that infrastructure provides. So why UEI? What do I mean by UEI? Why does Childress think we need yet another jargon word thrown out there into the literature? To start off with, Homo sapiens is becoming an increasingly urban species. We know that. We build cities as our habitat, and when we do that, infrastructure is the result. Now, the kind of infrastructure most people think of when they think about urban is the built environment, right? That's what we call gray infrastructure. The rest of the physical infrastructure in cities that is not actually the built environment, though, is what we are defining as UEI, all right? So UEI covers everything that's not physically built, from street trees to people's yards, from lakes and rivers to vacant lots to parks, right? It's all UEI, right? And so essentially, everything in the city that isn't built is UEI, and most of that UEI, almost all of it in fact, is either designed or is designed and managed. Now the trick here is that there are different ecological components to UEI, right? There's the terrestrial component, which is the most obvious to us because we are a terrestrial species, but all cities have aquatic components and all cities also have wetland components. And so we then have decided to differentiate the different types of UEI in a city using colors. And as I said, as a terrestrial species, the most obvious type of UEI for us is green. But again, all cities have various aquatic features. Aquatic ecosystems function very differently than terrestrial ones, and so we refer to this as blue UEI. But then wetlands, which are the most awesome ecosystems on the planet, by the way, are particularly awesome because they have ecological structures and functions that are both terrestrial and aquatic at the same time. And so wetlands are neither green nor blue, they're both, and it turns out if you're an artist and you combine those two colors, you get the color turquoise, right? And so that is the third color of UEI that we refer to when we think about the more natural stuff in cities. This is our conceptual framework that's guiding all of our research right now, and right there, front and center, in its own very almost turquoise colored oval, you can see urban ecological infrastructure. It is the structural bridge between the human realm on one side and the biophysical realm on the other, all right? The functional bridge between those two components then, going from the biophysical to the human, is the purveyance of ecosystem services, largely by that UEI. And then the functional connection between the human and the biophysical is the way that we design and manage UEI in the first place. So I'm going to go through quickly a couple of examples. There are lots of examples of UEI from our 20 years of long-term research that we've been doing here in Phoenix. but I was told I only had 45 seconds for this talk, and so I'm only going to give 2 of those examples. And the first one is from our long-term stormwater research. We focused this all along on the city of Scottsdale. And the story about stormwater management in the city of Scottsdale is interesting because back in the 50s, when Scottsdale was building itself out and turning itself into the Palm Beach of the West, which actually a couple of developers actually said that back then, there were some pretty bad floods. And so the city of Scottsdale did what most cities do when they're faced with flooding problems. They called the Corps of Engineers, and the Corps of Engineers came running in on its white horse, knight in shining armor, to save Scottsdale from itself and from water. And it said, we have the perfect solution for you guys. We solved Los Angeles' problem, we're going to solve yours. And the city of Scottsdale took one look at the Corps' plan and said, there's no way in hell you're putting an ugly concrete ditch through the middle of our beautiful city. And so they went back to the drawing board, and what they came up with in place of an ugly concrete ditch is this long, skinny urban park that you see right here. This is the Scottsdale Greenway, and this park is almost always green UEI, right? This is a terrestrial amenity by and large. It's an urban park. It provides huge numbers of ecosystem services to the people of the city of Scottsdale, and it's almost always green UEI, but every once in a while it rains in Phoenix. And if it rains enough, what happens is that the Greenway fills up with water. And it fills up with water because this is Indian Bend Wash. This is the lowest point in the city of Scottsdale. And so the answer to a concrete ditch was a park that is usually green UEI, but every once in a while it becomes blue UEI because it fills up with rainwater and protects the city from flooding while also holding that water in the city. Really cool story. The second example, of course, has to be an example of turquoise UEI because wetlands are the most awesome ecosystems on the planet. And this comes from some long-term work we've been doing at a large constructed treatment wetland in the West Valley. It's called the Tres Rios Constructed Treatment Wetland. It is just downstream of the largest wastewater treatment plant in the city or in the valley. It has 3 wetland components. We've been working in the largest one here, which is the sort of L-shaped one. It's almost exactly half vegetated marsh and half open water. And so this is the final treatment for effluent coming out of the wastewater treatment plant before it is discharged into the Salt River. We've been working out there for about 7 years, and among the many ecosystem processes that we've been quantifying on a bi-monthly basis, we've been doing very detailed water budgets, right? And so this is the only data slide I'm going to show, but I love this data slide because if you know anything about ecohydrology, this is a very dramatic slide. We do estimates for how much water is leaving that wetland through the plants, purely through the plants, to the atmosphere every day through the process of transpiration. All right? And if you look at this, you can see that in the hot summer months, we're talking about huge volumes of water. As much as 10,000 cubic meters of water a day are leaving from the plants, through the plants, to the atmosphere. Now, a cubic meter of water is about like that. 10,000 of those every day, right? This is a huge, amazingly huge number. And we thought, well, that water has to be replaced. It's got to be replaced from somewhere. And the only place that it could possibly come from is from the adjacent open water areas. And so we posed this idea that, in fact, because of the activity of the plants, all of this water going out this way, that water has to be replaced by a slow, gradual movement of water into the wetland, right? We termed it the biological tide. We've actually measured it. It is a perceivable flow of water into the wetland that is purely driven by the plants, right? This is the first time, to my knowledge, that surface hydrology in a wetland that is purely mediated by biology has ever been documented. This is cool because what that means is that putting this system in a hot, dry place, like we did, created this process that we weren't expecting that's moving even more pollutants into the marsh where they're being treated by the system. So, very cool example of a surprise that we found with our turquoise UEI. And now I think I may need help figuring out how to do this. Let me see. There's supposed to be a short video here because this, here we go. I'm going to let the charismatic system talk for itself.
The adolescent states were really rocky. We we were manhandling this place. And we got it under control, and part of it was trying to get the environment to stabilize itself to where it knew what it was, giving itself an identity. Desert productivity is limited by water availability. In aquatic systems, water availability is not an issue, and so more often than not, the productivity of the system is limited by one of two what we call macronutrients. And they're the same things that you find in fertilizer. They're nitrogen and they're phosphorus. In Arizona, the limiting nutrient is nitrogen. If you get too much of the nutrient that's controlling ecosystem productivity, the system becomes too productive, it becomes what we call eutrophic and polluted, you get fish kills, and it's no longer safe to drink. The water that leaves our houses and pipes when we take showers, we do laundry, we flush toilets, winds up at a very sophisticated wastewater treatment plant. There are maximum levels of nitrogen that the city is not allowed to discharge into the Salt River. The city could very easily have made the wastewater treatment plant across the street technologically able to get all of the nitrogen out of the water. It would have been very expensive and very energy intensive.
Just in facilities to match what they can do in their design parameter, it would probably be well over $5 billion.
Instead, they chose an easier route. We'll spend a little bit of money, a fair amount of money up front designing and building the thing, and then basically we just sit back and let nature do the work for us.
Tres Rios was built more as like a polishing tertiary filter. It turns around and takes our effluent, which has really good nitrogen removal, and it knocks it down even farther.
We were, as ecosystem ecologists who work in wetlands, we're very interested in understanding how this system is working, how it's doing the job that the city is expecting it to do. And so we thought, you know, if you put a wetland in a very hot, dry climate, it's going to be losing a whole lot of water to the atmosphere.
And that is what we were worried about, was that this increasing drawdown of water is going to concentrate whatever is in the water to stress out the plants, make it harder for them to do their job, and then obviously decrease the performance of the system.
For the first time ever, we documented what we call a biological tide. It's effectively a very gradual movement of water into the marsh that's completely driven by the biology of the plants. We have lots of evidence that if nitrogen gets into this marsh, it gets completely expunged from the water. This biological tide phenomenon that we found is doing a better job than if it was in a cooler place or a more moist place. So when you have a natural ecosystem or an ecosystem like this that's asked to do something that benefits humans, is providing an ecosystem service. That job of nitrogen removal was the ecosystem service of design. But what we saw happen out here was another ecosystem service that the city was not expecting. And that was that this place became an absolute mecca for wildlife, especially for birds.
For people in the Audubon and biologists, we weren't surprised at all. We firmly believe that in this situation, if you build it, these birds will come and they will use these resources. The Tres Rios is really key for water birds and waterfowl that come here to spend the winter.
There's a flock of 3 or 4 dozen white pelicans that came here to winter 3 winters ago, and they never left. So our little oasis of productivity in the Sonoran Desert is home to dozens and dozens of different species of wetland and aquatic birds, and that's really cool. Most of the water that's going from this system here and being discharged into the salt flows downstream, and it hits what's called the Lower Buckeye Diversion Dam.
And then that water is utilized for agricultural uses.
As we go into the future in recycling and reusing waters, that will always have this as being a component of it.
I have spent my entire career studying wetlands from a very holistic perspective. And so there's something very cool about working in a system that was specifically designed to do a job, and thanks to the birds and the other wildlife, turns out it's doing other jobs that we weren't expecting. So I love wetlands. It doesn't matter where they are, what they're doing, what they look like, they're amazing. Yep, that's it.
Very cool. So a great example of a pilot, right? That's sort of demonstrating what can happen when we understand a little bit more about the ecology and we can design the systems. And I think it's important to sort of recognize in these narratives and these stories that all of these organisms are our friends, right? That they're part of the process that we need, this green infrastructure of bringing it in. And there's also a lot of potential for us to continue to expand on the gray and those buildings, and how can they also contribute back? And that's part of what Generous Cities is saying is green infrastructure and blue and turquoise infrastructure enough, and what would it look like for our gray infrastructure to also be generous as well? And that's where we're hoping that biomimicry at many, many different levels not just contributes to the measure part of that, but also gives us some ideas and models to the surface area. How do we put that surface area to work in a variety of different ways?